Last class, we learned about electron configurations, orbital diagrams, effective nuclear charge, shielding, penetration, some other stuff like that. I'm going to go back to these diagrams of shielding and penetration because they are going to come up in some of our later material that we'll hopefully be getting to today. So one of the big ideas with shielding is that these electrons in our outer shell, whatever our outermost electrons are, because they're in a different layer, all of the electrons that are inside of them in these inner layers sort of block out some of the effect of the nucleus. And so in this case, we've got an electron on the outside. This is our third electron. Our nucleus on the inside has a 3+ charge, but because there's 2 electrons inside, we subtract away 2 of those positive charges. They're effectively canceled out by these electrons. And so that means that the electron that's outside is only experiencing a 1+ charge, and this is the effective nuclear charge, or Z sub EFF. And so this is an idea, this shielding effect and this effective nuclear charge is an idea that we're going to be thinking about a lot with some of our periodic table trends, which we will hopefully be getting to today. So I just wanted to remind us of that. Those outermost electrons we call valence electrons. So our valence electrons are those in the outermost principal energy level, the ones that are in the highest N number, like when we were doing these orbital diagrams. So for the orbital diagram for argon, our 3s and our 3p, these are both in the n equals 3 level, and so all 8 of these electrons would count for valence electrons. The rest of the electrons are what are called core electrons. So those are the ones that are in the inside. Those ones are going to be providing some of the shielding for our outside, or our valence electrons. So electrons in our lower energy levels, anything that's below our highest N number, are going to be our core electrons. So these shield the valence electrons. And valence electrons, it turns out, play a very big role in the way that atoms behave chemically as well as physically. It's based on the number of valence electrons. So elements in a column or a group on a periodic table have similar chemical properties because they have the same number of valence electrons. So our periodic table, at least for the main group stuff, is conveniently laid out so that everything in our groups 1A, 2A, 3A, or 13, all the way over to 8A or 18, these all have the same number of valence electrons. So everything that's under beryllium, Be, is going to have 2 valence electrons. Everything that's under carbon is going to have 4 valence electrons. Everything that's under fluorine is going to have 7 valence electrons, for example. We could come up with that. We can prove that to ourselves, sort of, or we could look it up if we look at the outer electron configurations. So for all of these, the outer electron configuration for our 1A is 1, is 1, is 1, 2, and 2. And then when we jump over to the other side with mostly nonmetals, we're starting to fill up our P subshell. And so for boron, we've got 2s2, 2p1, add one more when we get to carbon, and so we can see we've got the same number of valence electrons in these different columns. Helium is our one weird exception. Helium only has 2 electrons. So that one's a little bit of an oddball. But generally, for our main group elements, so if we exclude our transition metal elements that would show up here, when we're in a column, they're going to have the same number of valence electrons all the way down. So we can just memorize them or use this A designation, and that tells us how many valence electrons we have. Okay, so let's, as a review, a refresher, write an electron configuration for phosphorus. We want to identify valence electrons and core electrons. So first thing we need to do is find phosphorus on our periodic table. So phosphorus is over in group 5A. It's number 15. That 15 is the number of protons that it has. That also means that it's going to have 15 electrons. When we start an electron configuration, we need to start from the lowest energy levels. So 1s is our lowest. So starting off with our 1s, since n is our lowest value at 1, and s is the only available subshell or type of orbital that we can have in the n equals 1. So we start off with 1s. We can plop 2 electrons into our 1s. We have 1 orbital. Each orbital can contain 2 electrons. So we've got 2 that we can put in there. So minus 2 electrons. We've got 13 left to place. After 1s, we have to jump up to n equals 2. And s is going to be lower in energy than our next subshell, which is p. We've still got plenty of electrons. We can plop 2 more into there. That brings us down to 11 electrons, and up next is 2p. And then 2p is the last subshell or letter that we can have in our n equals 2. Our p orbital, or our p subshell rather, has 3 different shapes inside of it. Remember, it's those 3 peanut shapes, the dumbbell shapes, the x, z, y, the 3 different orientations that have this sort of a shape to them. Since we've got 3, and you can put 2 electrons in each, we can get 6 electrons placed into there. That will leave us with 5 electrons left over. After 2p, we have to jump up to n equals 3. And s is still going to be lower energy than p. We can fill that up by adding 2 electrons in. We'll have 3 electrons left over, and those will go into our 3p, since p is lower energy than d. So it'll be 3p3. And if I had been thinking about it, we could have just done our shortcut, but that's fine. So this would be our correct electron configuration for phosphorus. And then we want to identify the valence electrons and core electrons. So our valence electrons are going to be our electrons that are in 3s and 3p, since the n equals 3 is our highest level shell. So 2 plus 3, we've got 5 valence electrons. The rest of the electrons are going to be our core electrons. So we've got 10 core electrons. Everything in our n equals 1 and n equals 2 shells. If we had done the shortcut, where we take the previous noble gas and put it in brackets, then we would end up with something very similar. It would be the symbol for neon in brackets, 3s2, 3p3. We would still end up with 5 valence electrons, and then neon represents all of our core electrons. And since neon has 10, because it has 10 protons, it also has 10 electrons, so it would represent 10 core electrons. Questions? All right. So an easier way, I think I alluded to this last class, there's an easier way of remembering our electron configuration, our filling order, than memorizing. There's like a chart that we looked at, a graph we looked at a few times. If we break the periodic table into 4 blocks, those 4 blocks being S, P, D, and F, then when we are working in those blocks or moving past those blocks, counting up on the periodic table, that represents the filling of our quantum sublevels, our subshells, our shape types, so S, P, D, and F. The group number of a main group element is equal to the valence electrons, so that's a check that we can do to see how many valence electrons we expect to have. Again, this only works for main group elements. The row number equals the highest principal quantum number for whatever the element is. So if we're in row 3, like with argon, if we're at chlorine, then our highest n level is going to be 3, because that's the row that we're in. And that works going further down as well. There's a couple of places where it's a little bit different than that, but for the most part, and especially for our main group elements, that's our highest principal quantum number, or n number. So here are the blocks of the periodic table. We've got our S block in this light blue color. It's our first 2 columns, our first 2 groups, and helium. Helium also represents filling in an S subshell. And then we've got our P block. So when we're in this block, this far right section, we are filling in p orbitals. We've got our D block that's in the middle, that's our transition metals. So when we're working in this section, we are generally filling up our D shell. And then our nasty F block elements that got pulled out, the lanthanides and actinides, and usually sit below the periodic table. I highly recommend memorizing these block locations. It makes coming up with electron configurations a whole lot easier. So our first 2 groups are the S blocks. Notice that it's 2 wide. There's 2 elements width. How many electrons can we fit into our S subshell? We've got 1 orbital. 1 orbital can hold 2 electrons. And so our S block is 2 elements wide, because that represents 2 electrons that we can put into our S block. Our P block is 6 wide. We've got 3 orbitals with 2 electrons each as a maximum, which is the reason that it's 6 wide. When we move to our D block elements, we've got 5 orbitals. 5 orbitals with 2 electrons each means that we have 10 electrons that we can put into our D block, and so our D block is 10 wide. For our F block, we have 7 orbitals with 2 each, and so that's why our F block is 14 wide. So if you can remember S, P, D, and then F down below, we can use this to fill in electron configurations, come up with electron configurations much more easily. And then a little pop quiz, where do all these blocks go? The square hole. Thank you. It's a dumb joke about blocks going in the square hole. Anyway, so the way that we can write electron configurations from our periodic table, we want to start with our inner electron configuration, our shortcut. So we look at what is our previous noble gas. It's neon. So we write the symbol for neon in brackets, and that represents everything that neon has. It's the complete n equals 1 and n equals 2 subshells. And then to get past that, so building off of neon, we look at what's next on the periodic table. Well, we're in row 3. So our n equals 3. And the first block that comes up is S. So we're working in 3s. Since we're trying to get the electron configuration for chlorine, we can see that we're past the S block. So the S block is going to be full, where we've got 1, 2. So it's 3s2. We skip over the D block, and now we're in the P block, still in row 3. But we're in the P block now. And we count over. How many spots are we in? We're 1, 2, 3, 4, 5. We're in the 5th spot. So it's 3p5. And that's our electron configuration. You can do this for any element. Questions on that one neat trick? Okay, using our periodic table, let's figure out the electron configuration for bismuth. Bismuth being way down here. There's a couple of things that I'd like to point out before I send you on this adventure of trying to figure out the electron configuration for bismuth. First thing, what n number does, what n does D appear in for the first time? What's our lowest n number that has the D subshell in it? Huh? It's not 5? D has 5 orbitals. It's got 5 different shapes. D is represented by L equals 2. Where's the first time the lowest n number that L equals 2 is valid? 3. So we would expect, you might expect, right, if we're looking at our third row, well, there's no D orbitals there. Our first row of our D block is actually in n equals 4. So scandium, we're filling in 3d1, even though n equals 4 is the row that we're working in. So you have to subtract 1 from your row number to get the n value for your D block. Our lanthanide and actinide series represent our F block. What color was the F block? It was green. Right, so our F block shows up for the first time in n equals 6. But this row that starts with lanthanum, cerium, whichever, no, not you, Siri. This row represents 4f, because n equals 4 is the first place that our f orbitals show up. So for D block, n equals row minus 1. For F block, n equals row minus 2. Keeping that in mind, go ahead and see if you can come up with the electron configuration for bismuth. All right, so our electron configuration for bismuth. If we want to save ourselves a bunch of time, we want to use our noble gas shortcut. So we're going to look at what's the previous noble gas. It's xenon. So we take Xe, put it in brackets, and that represents everything in row 5 and up. After xenon, we get to row 6. So since we're in row 6, n equals 6, what block are these first two columns? S block. So we're doing 6s. We are past the S block, and so we are going to have a full S block. There's 2 spots, so 1, 2, 6s2. We also have than the D block that we run into. And this first row, which is in n equals 4, is our 3D block. So yttrium would be the start of our 4D, lanthanum would be the start of our 5D. So we come up to 5D. We are past our D block, and so it's going to be full. There's 10 spots in the D block, so it's 5D10. We also have in there this cutout that represents our F block down here at the bottom. And that's going to be 4F, and we are past our F block, and there's 14 long in our F block, so it's 4F14. And then we're back into n equals 6 P block. So 6P, since this whole square-ish shape is our P block, and we are in the third spot, so 1, 2, third spot, so it's 6P3. So our full electron configuration with the shortcut would look something like this. I might have the order of the D and the F orbitals different. I think there's some different ways of writing it. Arguably, the most important part is that we got 6s2, 6p3, since those are our valence electrons. The rest is core electrons. Questions about that? Cool. Okay, let's do some more electron configurations. We've got electron configuration for chlorine. We've got one for silicon. We've also got strontium and oxygen. I'll give you some time to work on these. These are, I would say, considerably easier than bismuth. All right, our electron configurations. We've got, up first, chlorine. Chlorine, the previous noble gas, is neon. And so we are going to take the symbol for neon and write that down to use our little shortcut. And then we look at what's after neon. What's after neon is sodium with row 3. Since it's row 3, we are in 3 for our N, and our group, or our block, is S. So 3S. We are past it, so 1, 2, 3S2. And then we skip all the way over to our P block. And since it's P block, we're still in row 3, so it's 3P. And we are in the 1, 2, 3, 4, 5 spot, so it's 3P5. For silicon, neon is our previous noble gas again. We are still past the 3S section, and now we're in 3P. 3P, we are in the second spot, so it's 3P2. For strontium, our previous noble gas is krypton, so we write the symbol for krypton in brackets. We are in the S block in row 5, so 5S. And we are in the second spot in the S block, so it's 5S2. For oxygen, taking a shortcut is almost no shortcut at all, but our previous noble gas is helium, so HE in brackets. We are now in row 2, and up first comes the S block with lithium and beryllium. We are past those, so 2S2. And then we jump over to our P block. We're in row 2 in the P block, so 2P. And we are in the 1, 2, 3, 4th spot, so 2P4. questions about any of those electron configurations? Our main group elements tend to have pretty normal electron configurations, but there are some issues that rise up when we are in other groups. So when we're in our transition metals, for example, because of the way that sublevels work and the splitting and all that sort of fun stuff, the 4s fills before the 3d. It's not a large difference in energy though. So there are two energy levels that are relatively close to each other, with 3d being a little bit higher in energy. Some of our transition metals have weird electron configurations where our NS, so our S shell doesn't fill before the D shell, or it doesn't fill at all. And these are some of those odd electron configurations. So chromium, copper, molybdenum, ruthenium, palladium all have weird electron configurations. In the case of chromium, what we would expect is 4s2 3d4, since it's the fourth spot in our D block. So we'd expect it to be D4. What we find is that it actually is 4s1 3d5. So it steals one out of the S and puts it into the D instead, so it's 3d5. We see a similar thing happen with copper, where we expect it to be 4s2 3d9, since it's in the ninth spot, the ninth position in our D block. And that does the same thing. It also steals one from S and puts it into the D. So we've got 3d5, 3d10. So this represents half full and full D shells, or D subshells. Similar thing happens with molybdenum. Ruthenium is a little bit weirder. Palladium instead steals 2 to fill up its D subshell. I don't expect you to have these memorized. The chromium and the copper ones are ones that I might expect you to know, and I think we have, nope, we don't have an explanation of that, so never mind. But the reason for these being 3d5 and 3d10, if we look at our expected, we've got 4s2 3d4. This is what we would expect to see for chromium. And what we actually see is 4s1 3d5. So it turns out that it's more energetically favorable for this electron to jump over into the 3d. And because of all of these having the parallel spin, that lowers the energy enough that this is more advantageous than having it in the 4s. And then the same thing happens for copper, just with all of them being paired up. So those are kind of interesting. Some other stuff that our quantum mechanical model explains. The chemical properties of elements are periodic because the number of valence electrons is periodic. This is a big driving force in the way that our periodic table is constructed. So elements in the same column have similar properties. That's also why they have similar group names, or the same group names. So alkali metals, alkaline earth metals, halogens, noble gases, and so on. The elements in a period show how a pattern repeats. If we're looking at the rows, we see the pattern repeat, especially in our first 2-3 rows. Quantum mechanics explains this because the number of valence electrons is the same, and the types of orbitals that they occupy are also the same. It's just we've added a shell on top of that. So for example, our noble gases, all of our noble gases have 8 valence electrons, which represents a full outer shell, which is especially stable. They don't have anything to fill. They've got this good symmetry stuff going on, good parallel spin things happening. Helium and neon are basically inert. They really do not like to react with anything. The rest of our noble gases also don't like reacting with stuff. Helium, neon especially so. Atoms with 8 valence electrons or 2 for helium are especially stable. When a quantum level is full and n level is full, the overall energy of the electrons is lowered because of all of those parallel spins. So the reason that noble gases are so non-reactive is because their electron configuration is especially stable. Stable and low energy go hand in hand. They're synonyms. Our alkali metals, if we think about our periodic table as wrapping around, our alkali metals are just one spot over from our noble gases. So if we moved over our noble gas column or our alkali metal column, it would be right next to our noble gases. We've just added one more electron. And so for our alkali metals, because they only have one electron in their outermost shell, if they lose that one electron, then they basically revert to being a noble gas. If they lose their one valence electron, they gain noble gas stability. Or noble gas configuration, which is especially stable. And as it turns out, it's relatively easy to lose that one electron. Electrons can pop off and pop back on, and when you're just losing one, that's relatively easy. And when they lose one electron, they form a 1+ ion. So that's the reason all of our alkali metals, our first column or group, forms 1+ ions, because they lose that one electron. Halogens are the other side. So halogens are located right next to our noble gases, but they are one electron short. So they're in the 5th spot. They're a 2s, 2p5 in the case of fluorine, or 3s2, 3p5 in the case of chlorine, and so on. And so to get that noble gas configuration where all of their electrons are synced up, they're paired up, you just have to gain one electron. So gaining one electron gives or confers noble gas configuration, which is especially stable. Basically, a way that we can think about it is most of our elements, they're generally trying to be more like noble gases, where they've got their electrons synced up. So they move the number of spaces, they gain the number of electrons or lose the number of electrons they need to get that noble gas configuration. So we get anions with one negative charge for our halogens for gaining one electron. There are other metals and nonmetals that form one predictable ion. Our group 1A, 2A, 7A, 6A, etc., all seen here on this chart. I don't know what this is all about. I guess the row numbers were wrong in the book, maybe. Who knows? So these are the ions that form with predictable charges. Notice all of our 1As, they're losing one electron to become like a noble gas, and so they're all 1+ charges. Our 2As, they're all 2+ charges because they would have to lose 2 electrons to get that noble gas configuration. On the other side with our nonmetals, they have to gain 1, they have to gain 2, or they have to gain 3 spots, 3 electrons to get noble gas configuration, and then they're especially stable. So that's the reason that we can just memorize a lot of those. Basically just memorize 5 or 6 things, and then that unlocks, half of the elements that we have to memorize their ions, or half of the things that we have to memorize their ions. This is basically just saying what we were talking about, and this is the other side. So anions get formed when nonmetals gain enough electrons to have 8 valence electrons, an octet of electrons, which is the noble gas configuration, electron configuration. So it gets full s and p orbitals. Sulfur atom has 6 valence electrons. When it becomes the s2 minus anion, it's got 8 valence electrons, just like argon. For our cations, the cations are formed when the metal atom loses all of its valence electrons, 1, 2, or 3, and this results in a lower energy level valence shell, and this usually is exothermic. You've got to put energy in to knock those electrons off. So magnesium, for example, removes or loses the 3s2 valence electrons, and then it becomes basically the same configuration as neon for its electron configuration. Questions about electron configurations, orbital diagrams, blocks? Okay, it is trend time. So atomic size can be defined in a couple of ways. One way that we can define atomic size is non-bonding atomic radius or van der Waals radius. So for things like krypton, where they don't bond, they just sit next to each other, the atoms sit next to each other, or metals would be in a similar situation. We can define the non-bonding atomic radius, the van der Waals radius, as half the distance between the nuclei. So there's going to be this distance. Maybe red shows up better. That's not red. There we go. All right, we've got this distance between the radius, or between the nuclei. If you take half that distance, we can define that as the atomic radii, because that should be about the distance from the nucleus to the edge of that atom, assuming that they're the same atom. There's also the bonding atomic radius, so things that bond, or the covalent radius. Covalent, like in covalent compounds, like molecules, where they're sharing electrons. In non-bonding radius, they're not really sharing electrons, they're just sitting next to each other. Our bonding atomic radius for nonmetals is going to be half the distance between 2 of the atoms bonded together. For metals, it's going to be half the distance between 2 of the atoms next to each other in a crystal of the metal. So we can see, because these are bonding together, we've got overlap of the electron clouds. That's what the circle shape is. So we've got some overlap. We take the distance between the nuclei, we divide it by 2, and that gives us our radius. Atomic radius is an average radius, and this is based on measuring lots of different elements and compounds. So this is more of a general term. You can make measurements, like with krypton and with bromine, you can make these individual measurements with one particular element or one particular molecule, but it only represents the radius for that one particular situation. And so we use instead the atomic radius, which is just saying, like, in all of the places that we've seen it, kind of on average, what do we expect, or what size is it? So this is more general, and this is always going to be smaller than the van der Waals radius, since it includes bonding radii. radii being the plural for radius. So if you look at our van der Waals radius, right, there's no overlap, but when we've got a covalent radius or a bonding atomic radius, they're overlapped so the nuclei are closer together versus a van der Waals radius. So we are going to be talking about atomic radius. So that's, again, like the average, the overall. So atomic radius increases as we move down a group. So if we're moving down on the periodic table, our atomic radius increases. The n number is increasing. Our principal quantum number is increasing. So we're adding new electron shells. So we're adding new layers of electrons. And this is sort of like, if you imagine, there's like the videos of people, I wore the most t-shirts in the world and they've got like 500 t-shirts on or something. Every t-shirt they add on makes them bigger. Every electron shell that you add on makes the atom bigger. So here we've got a graph of atomic radius. We've got our atomic number on the x-axis. So as we're moving left to right, we're moving through the numbers on the periodic table. And our radius is on the y-axis, so the higher up we are, the bigger our atom is. And if we look at our noble gases or our alkali metals, we've got helium, neon, argon, krypton, xenon. They're getting bigger as we're moving down the noble gas column. And for our alkali metals, our first column, it's the same trend. It gets bigger every single time that we move down to the next alkali metal. However, atomic radius decreases as we move across a period. So as we're moving from left to right across the periodic table, we generally have a decreasing atomic radius. So we're adding protons, we're adding electrons, and it's getting smaller, which is probably not what you expect. Any ideas? We're adding more stuff in, yet it's getting smaller. Well, it turns out that it's the adding the protons and the electrons that causes it to get smaller. So remember, we had talked about shielding a little bit at the start of the lecture. When we've got multi-electron systems, electrons are attracted to the nucleus. They're also repelled by each other. Our outer or valence electrons are shielded from the nucleus by the core electrons. So our outer electrons experience a lower effective nuclear charge. They don't get the full force of the nucleus because there's electrons in the inner shells that protect the nucleus. So here's that picture, diagram, right? Our nucleus has a 3+ charge, but we've got some core electrons, and those effectively block out the equivalent amount of positive charge. So since we've got 2 negative charges and 3 positive charges, this valence electron only feels about a 1+ charge. Now what if we change the number of protons, we change the number of electrons? So that's where effective nuclear charge is helpful for thinking about this trend. So our Z effective here is our effective nuclear charge. Z is our actual nuclear charge, our number of protons. S is the number of core electrons. So we take the number of protons minus the number of core electrons, and that tells us what the effective nuclear charge is. And our valence electrons, our outermost shell, does make a really small contribution to shielding, but it's not like whole number significance. So we're just going to use this effective nuclear charge instead. So we're going to take two elements and look at them as an example. We've got nitrogen and argon. So for nitrogen, we've got how many protons? Nitrogen has 7 protons. Its atomic number is 7. And it has core electrons that are equivalent to the same number of electrons as the previous noble gas, in this case neon. So 7 minus 2, its effective nuclear charge is 5. So all of the valence electrons are experiencing effectively a 5+ nuclear charge. For argon, our effective nuclear charge, we take the number of protons that argon has, which is 18, because that's its atomic number, and we subtract the number of core electrons represented by the previous noble gas, in this case neon. So neon has 10 electrons, meaning that argon has 10 core electrons. So argon has an effective nuclear charge somewhere in the range of 8+. So imagine if we've got our outermost shell of electrons, if they're experiencing a 5+ nuclear charge versus an 8+ nuclear charge. The 5+ nuclear charge will be drawn in a certain amount. If you add a couple more protons to increase that, that's going to cause some shrinkage. It's going to cause those electrons to pull in more. So valence electrons experience more effective nuclear charge across a period or row which causes them to get pulled in more. We're operating within the same outermost shell size and getting a little bit of a suction or a magnetic pull effect in as we move across the row because of the increased charge, the increased effective nuclear charge. So our trend for atomic radius, it increases as we move right to left and top to bottom. It increases as we move down a column because we're adding shells to our atom, adding layers to our onion. And as we're moving across a period, our effective nuclear charge increases, but we haven't added any more shells. And so it's going to get smaller as we move right to left. I think it's usually more helpful to talk about the way that it increases. So it increases right to left, top to bottom. Any questions about our radius trend? For our transition metals, it's roughly the same size across the D block because the effective nuclear charge is about the same. Probably won't ask you any questions about transition metals for atomic size. But it does increase as we move down a column. It's just the left to right doesn't really make much of a difference. Okay, for each of these, let's choose the larger atom in each pair if we can. So for tin or iodine, which one's going to be bigger, tin or iodine? tin on the left, iodine on the right. It's going to be tin. So we get a slight decrease as we move left to right because tin has 4 valence electrons. It's going to have an effective nuclear charge of 4. Iodine has 7 valence electrons. It's also going to have an effective nuclear charge of 7. That effective nuclear charge that increases is going to cause the electrons to pull in slightly. That's why we get shrinkage as we move left to right. So things that are further to the left are going to be bigger. So tin is bigger than iodine. How about germanium or polonium? Germanium on the left, polonium on the right. Which one do we think will be bigger? We've got a guess for polonium. So we've got some competing trends. On the one hand, right in the left to right trend, germanium's further to the left, so it's not going to experience that sort of shrinkage effect. But polonium is further down, and so we've added 2 new shells because it's 2 rows down. I think it's safe to say that polonium is going to be bigger here. Because we added 2 shells. Which probably overpowers, almost definitely overpowers, the difference in effective nuclear charge, which is just 2. It just causes a little bit of shrink. So polonium is probably bigger here. And then our last one for this trend, chromium or tungsten, wolfram. Chromium on top, wolfram, tungsten on the bottom. Which one's going to be bigger? This one, it's definitely tungsten. Tungsten has added 2 shells or layers of electrons, so it's absolutely definitely bigger. It's further down on the periodic table. We also have electron configurations for ions, something that you probably didn't cover in your Chem 20. So as a reminder, we've got anions and cations. Cations, cats have paws, cations are positive. Anions, I think the worksheet just has a picture of onions and being sad, and that being bad. Anions are negatively charged. So anions are formed when atoms gain electrons. So you have to add electrons to the electron configuration. 1 for each negative charge. Cations form when atoms lose electrons, so they have a net surplus of protons. So for these, we have to remove 1 electron for each positive charge. So for example, our aluminum atom, if we've got Al3+, we're taking off all of our valence electrons, our 3s2, 3p1, they're gone. We strip it down to having the neon gas configuration, which has our 2s2, 2p6. We know that it's going to be aluminum 3+, and for our main group elements, it's going to form a noble gas configuration, either adding electrons to get over to it, moving left to right. All of our nonmetals are going to form negative charges. Our metals have to move left to strip off the valence shell to get there. Our transition metals, however, we don't know what charge they're going to form. And so we would have to be told what the charge is. Now for transition metals, we first want to remove the valence electrons. So as we're moving across our periodic table, let's say that we're looking at vanadium, the third entry in our D block. So the way that we would fill up for our electron configuration, we've got potassium and calcium in row 4 that are before vanadium. All right, so that's our 4s. We're past our 4s block. Then we add in, when we get to scandium, our 3d1, titanium 3d2, vanadium 3d3. So vanadium, for example, 4s2, 3d3. If we have vanadium plus, if we take off one electron, even though we're filling core electrons here, even though this is the most recent thing that we filled, we still have to take off our valence electrons first because that's our outermost shell. So that's where the electrons are going to be easiest to pull away. So V plus, if it exists, would be 4s1, 3d3 for our outermost electron configuration, not including our argon configuration. So we're always going to be removing the valence electrons first. Draw some arrows at that. So if we are looking at iron, this is our iron electron configuration. So we've got 4s2, 3d6. If we have iron 2 plus, what we've done is we've removed the 4s2. So we take off the 4s2. Notice that no 4s2 here in our Fe2 plus cation. And then once we get to our 3 plus, our ferric ion, then we take off one from our 3d subshell. So it goes from 3d6 to 3d5. So our orbital diagram for Fe3 plus would look like this. We've got our empty 4s and our 3d is half full. So 3d5 and an empty 4s. And the reason that we talk about this is so that we can talk about atoms or ions being paramagnetic or diamagnetic. So paramagnetic has unpaired electrons, and paramagnetic ions or atoms will be attracted to a nuclear field. And this is due to the unpaired electrons. They can generate a magnetic field because they've got spin. So like for our Fe3 plus, our D shell, right, looked like this. Our 3D looked like that. We've got all of these unpaired electrons with plus 1/2 for each of their spin values. And since these all have spin, we get some magnetic field effect. In diamagnetic atoms or ions, all of the electrons are paired. So something maybe with a full D shell. And since we've got upspin and downspin together, we've got our plus 1/2 and our minus 1/2. We've got no net spin. And so it doesn't react to magnetic field with attraction. It gets slightly repelled. The big things to memorize, probably just memorize these, right? Our paramagnetic means that it has unpaired electrons. Diamagnetic, di like 2, it's got both directions. Diamagnetic means that all of our electrons are paired. Okay, let's write electron configurations and orbital diagrams for these ions. I'll do the first one, and then we'll do the other one next class. So cobalt 2+. First thing we want to do is find cobalt on our periodic table. It's in the middle of our D block. And its previous noble gas is going to be argon. So cobalt, being in the D block, is past the S block in row 4. So it's going to have 4s2. This is just for cobalt. We'll do the 2+ after that. And then we have to count what spot is it in our D block. Remember, this is 3D because it's our first row of D. 3D, it's the 1, 2, 3, 4, 5, 6, 7th spot. So it's 4s2, 3d7. When we go to cobalt 2+, are we adding or removing electrons to get that positive charge? We're removing. We've got a 2+ charge, so we're going to remove 2 electrons. Which 2 electrons are we removing? We can remove them from the S or the D. What do we think? It's got to be from the S because it's got the higher number. So we've got 2 electrons in our 4s. We just get rid of it, and we're going to have just 3d7. I'll write in an empty block for our 4s, and then for our 3d, we've got 3d7. We need to fill them in singly with parallel spin first. So 1, 2, 3, 4, 5, and we've got 2 more, and we can fill these now in with parallel spin. Is this paramagnetic or diamagnetic? Yeah, this is paramagnetic. We have unpaired electrons. Questions? Okay, then we'll stop there.